Standard practice in the carbide industry now is to sandblast the parts, which gets off a lot of the carbon but may smear it. Tungsten carbide typically needs to be treated to be wettable. As a test, if you get somebody and says your braze alloy won't wet on the tungsten carbide, if they take that piece of tungsten carbide and hold it to a bench grinder, take a Dremel with a sander on it or a cutting tool or anything, and just abrade away the surface of it till you get a nice shiny surface, and then have them try and wet it. And the wetting test is to take a real small piece of wire and some black flux and put it on and heat it and see how far it spread. Here's our high-tech test instruments. These are WD-40, acetone, some black ink and Easy Off, and a saw plate. So we colored the WD-40 with ink, put it on the saw plate, and then we took the acetone and wiped it off. And this is what you get after rinsing. This is the acetone side with the wipe. You can see the white marks here. And this is what you get with the Easy Off oven cleaner. And with the Easy Off oven cleaner, you get a much cleaner surface. And that's where we got. That's what this surface look. These two surfaces look like after we melt the braze alloy on it. So I've been telling people to clean. For better than 20 years, I've been trying to get people to clean the parts. It's still the #1 problem we have is cleanliness of the brazed parts. If you're brazing carbide, then the #1 problem is probably the carbide preparation. And carbide companies look at the whole piece of carbide. Depending on how well the carbide's made, it can have pools of the cobalt in it, it can have big grains, it can have contaminations, it can have holes in it. So that's what they inspect for. They typically don't care very much about the surface. And when a guy calls me because the carbide won't braze, typically he's called Kennametal first, or whoever supplied the carbide, that has said that's a fine piece of carbide. And by their standards it is, because they're looking at the whole piece. You guys are looking at the top couple microns. Bag 7 to 56%. Is a popular braze alloy with hobbyists. It's easy to use. It wets out well. People used to use bag 3, which is a 50% with cadmium, which is a beautiful braze alloy for brazing carbide, except it has cadmium in it. The cadmium thing got to be a big deal in the tool industry because about 15 years ago, Systematic Saw had used a lot of it. They were an old plant. The cadmium fumes readily. Okay, it's like water steaming before it boils. Cadmium and zinc both fume before they boil. But over the years in the Systematic Saw plant, the cadmium would come out, deposited on the overhead beams and whatnot. WSHA, which is Washington State's version of OSHA, came in, found it, fined Rich Budke, the owner, 30 grand, cut it to 10 grand if he would go out and speak. So to save 20 grand, he went out and told everybody about the dangers of cadmium. Cadmium is dangerous if you inhale it or if you eat it. If you don't inhale it or you don't eat it, it's not going to hurt you. Be real careful about telling people cadmium won't hurt them. It can. But the secret there is not to use a bad alloy, it's to control the exposure. But when people found out they couldn't use the 50% with cadmium anymore, they went to a cad-free. And they switched to a 50% cad-free because that was their understanding. If you're using a 50%, then you switch to a 50% cad-free. They know nothing about the chemistry or how the braze alloy joints work. We did tests with Weyerhaeuser and Systematic and Cascade Southern using a Sharpie impact test. And what we did is we built little sections of saws with one tip on them. And a Sharpie impact tester, you bring a hammer down, hit the tip, and then measure how far it travels after the tip breaks. And as near as we can tell, and this is really rough, but a 50% braze alloy, cad-free, is about 30 to 40% weaker than the 50% braze alloy with cadmium. So we started promoting the 49% braze alloy with manganese is as strong as the bag 3, the 50%. It's harder to use. It's not as pretty and doesn't flow as well, so people have a strong tendency not to use it. If they are getting weak joints brazing carbide, see if you can get them to use the 49% with manganese. The 56% with tin is even weaker yet, but that's a great alloy for hobbyists. We sell little brazing kits for what, 20 bucks? You get some black flux and directions and a couple of feet of braze alloy in it. We include the 56% in there because cosmetically it's nice, it's easy for them to use, and it's more than strong enough for most hobbyist applications. It's not strong enough, it's not the strongest alloy to use for brazing carbide tools. Braze joint thickness. Braze joints, the thinner the braze joint down, according to Lucas Millhop, down to about 1/1000. The stronger the braze joint is in a tensile, a pull. The thicker the braze joint is, the better a job it does at relieving stress. And when you're brazing carbide to steel, the steel has a coefficient of expansion roughly 2.5 or 3 times that of carbide. You sometimes hear as much as 4. But what happens is when you go to put the tip in the saw notch, if you heat it up, then when you draw the temperature away, it locks in place, and as the steel keeps shrinking, it wants to bow that carbide and put heat stress in it. We'll show you, I think I've got some pictures coming up on that where we show you heat stress on it. We recommend about 3 to 5 thousandths of an inch between the steel and the carbide, and that's more than enough. As I say, that's more than enough so that the braze joint holds, but when you beat on it, either the carbide breaks or the steel rips. Improper brazing temperature. We sell pre-tin tips, which means we put the braze alloy on the carbide, ship it out to people who then put it in the saw. As near as we can tell, by pre-tinning, even with our equipment, we raise the reflow temperature of the alloy by, call it 30 degrees Fahrenheit. So an alloy that flows, bag 3, which flows over a range of 1170 to 1270, I don't care, you're the lady, we'll move over here where you don't have to crane, which flows from 1170 to 1270, if it's been heated once, no matter even partially heated, you'll need another 30 degrees. We also recommend brazing at a temperature about 50 degrees Fahrenheit over the temperature range given by the manufacturer. The only place I've ever seen any real studies done on this was in a NASA tech brief. With silver brazing alloy, they used the figure 50 degrees. We find that that's a nice rule of thumb for these people. You guys know what a temple stick is, by the way? Okay. Temple stick, they're sold in welding supply shops. They come in a steel tube and it's like a chalk thing, and they come in temperature ranges. You can take a temple stick and you rub them next to where the braze joint is going to be. When the chalky stuff in the temple stick melts, you know you've hit that temperature. And it's probably about the best way we know to actually measure the brazing temperature and for the guys to see what they're doing. We have color charts. We used to give out the color charts, but they don't work real well in most shop atmospheres because of problems with the lighting, problems reading and whatnot. They need to get the parts with the braze alloys we're talking about in the 1150, 1200 Fahrenheit range. We're telling them to get them red, maybe dark to dark cherry red. They'll go a little bit, and then if we do that, they'll go a little beyond it. They do not want orange, and they do not want yellow. And you'll see guys trying to braze. If they see any orange, if it gets real bright, it's wrong.